Radioactive decay. That's what we're going to talk about. So, let's start with a strong nuclear force. Let's go down to the nucleus of the atom. What do you find in the nucleus?
Protons and neutrons.
Protons and neutrons. Neutrons are charged how?
Zero.
No charge. They're neutral. Protons are charged positively. So, and you guys know that similar charges repel. So the protons do not want to be in that nucleus together. They want the electromagnetic force or the Coulomb force is repelling them. They want to be ripped apart, but they're not. There's another force that's even stronger than the Coulomb force holding them together, and that's the strong nuclear force. Strong nuclear force is the strongest of the four known fundamental forces, but it's an attractive force between nucleons. So protons exert the strong nuclear force, and neutrons exert the strong nuclear force. That's one of the reasons why they're both in there, because the neutrons can help overpower that Coulomb repulsion that's happening. It's a very, very strong force, but it's very short range. Very short range. It only, less than 10 to the negative 15th of a meter. And remember, 10 to the negative 15th of a meter is about the diameter of the nucleus. So this force doesn't even reach across the nucleus. It only really works well among neighboring nucleons. So it's a force that one neutron can exert on the neutron right next to it, but if it's a big nucleus, it's not going to really exert it on the neutron on the other side of the nucleus. It can't reach that far. It gets very weak very fast.
So what if it's like a high intensity?
Then there's nothing to worry about. It's just protons sitting there. But then if it's like if it's a deuterium, a proton and a neutron, the strong nuclear force is kind of holding those together. They're right next to each other. Small nuclei, it's pretty strong. That's why smaller nuclei tend to be relatively stable. Really big nuclei, this force it gets very weak very quickly, and that's one of the reasons why large nuclei tend to be less stable. They tend to decay.
Wait, why would the nucleus want to get away from each other if it's not positive? What causes that?
So we're talking about nuclei now, and guys, I just want you to make sure that you understand the shift we made. The last class when we were talking about spectral lines and all that stuff, we were looking at atoms as a whole, looking at the electrons and their orbitals and what electrons do when they change orbitals. Now we're delving down into just the nucleus, so we're getting into it even deeper. Now, some nuclei are stable and some are not. And a stable nucleus is one that's going to basically keep its form for a very, very, very long time. An unstable one will break down and become something else. And basically, the smaller nuclei tend to be the most stable ones. For the small nuclei, the ones that up to an atomic mass of about 30, which would be an atomic number of about 15, they will be stable if they have the same number of protons and neutrons. Okay, so like carbon-12, 6 protons, 6 neutrons, it's relatively stable, right? Helium, 2 protons, 2 neutrons, it's pretty darn stable. So up to about phosphorus, that's true. You'll usually find the same number of protons and neutrons. Once you get into the larger atoms, the larger nuclei, you need more neutrons to counterbalance that repulsion of the protons. So the stable nuclei for the larger atoms tend to have more neutrons than protons once you get above an atomic mass of about 30. And once you get really big, like above atomic number 82, they're not stable. Everything above that one breaks down. So you look at the periodic table of the elements, and you notice the ones at the very end, the really big ones, those aren't even shaded in. They're outlined letters, and that means that they were created in a laboratory. They're very unstable. They don't stick around for very long.
Is it possible, after billions of years,
Let's take a look at a picture of what this is telling us. Here's the diagram of it. So this is an interesting diagram. It's actually every one of the red dots are nuclei, and I think that they're mostly pretty stable nuclei. And notice that for the small ones, the red line that's drawn would be if you had the same number of protons and neutrons. So for the small ones, they have the same number of protons and neutrons. But when we get up into the bigger nuclei, you tend to get more neutrons than protons, and that's why these red dots leave that red line. And that's what brings stability, because a neutron will exert the strong nuclear force, will add more attractive force, but it's not going to add any sort of repulsion electrostatically because it's not charged. So that's one of the reasons why it's happening that way. Okay, the weak nuclear force. The weak nuclear force is the other of the 4 fundamental forces that's happening down inside the nucleus. It's the second nuclear force. It's weaker than the strong nuclear force, so it's appropriately named, I suppose. And it shows up in certain types of radioactive decay, most notably what we're going to call beta decay. You don't need to know a whole lot about it in this class. It has to do with quarks and things like that, and constituents within the nucleus. So just know it's there. That's about all we need to know about it. Okay? Let's talk about radioactivity then. That's really kind of the bulk of what I want to get to today. And it was first discovered in the late 1800s. And it was discovered by this guy, Henri Becquerel. And it was kind of an accident. They were discovering, at that time, there were a lot of people that were experimenting with these rock samples that were unusual. And they were mostly notably unusual in that they stayed warm most of the time. And that was like really cool. People didn't know why they stayed warm. But they were like, wow, that's really neat. And people were doing different sort of studies and experiments on them, and no one knew what it was. But Becquerel, he did an interesting thing where, totally by accident, he had placed these rock samples in a part of his lab where he had photographic film. And back in the olden days, before digital cameras, and you used photographic film, you guys probably know this, but the way you exposed it was by exposing it to light really quickly. And it would change the chemicals in that film, and that's how you make pictures. So when you had photographic film, you stored it completely light-free. You'd put it in these containers where light couldn't get in, so otherwise it would ruin the film. So he had these rocks on top of the container. He had film inside of it. It was probably like a file cabinet or something. And then he went to use the film later, and he noticed that when he pulled it out and did stuff with it, there were areas where it looked like it had been exposed to light, but it never had. And he was able to make the connection that somehow these rocks were exposing his film, even though they were in totally, different containers and stuff. And he thought, that's pretty weird. And he called it radioactivity. Didn't know what it was, but he's like, these rocks are radioactive. They're giving off something. They're exposing my film. It's kind of cool. A lot more research was done very quickly by a lot of people, but most notably Marie and Pierre Curie. You probably heard about them before. They did a lot of incredible work, but a lot of the research was done on radioactivity, and they discovered new radioactive elements. And so they got to name them. That's kind of cool. When you discover a new element, you get to name them. So they were the ones that discovered radium and polonium. The stuff that Becquerel was working with was uranium, and then these guys discovered radium and polonium. Radium was named because of radioactivity. What do you think polonium was named after? Poland. And I think Marie was Polish, I believe, if I remember correctly, and Pierre was French. So she named it after her homeland of Poland. So Taggart asked if they died from dealing with all this radioactivity, and the answer is yes, they did. But Pierre and Marie Curie really did a lot of research in radioactivity. Pierre, he died not from the radioactivity. He was run over by a horse cart before the radioactivity could kill him, and he died that way, which I don't know exactly how that would happen, because you don't think a horse cart would be moving that fast, but evidently something happened, and But Marie Curie, yes, she died from radioactivity exposure and cancer kinds of things. Don't know. I don't know how old they were. So these guys did a ton of research in the realm of radioactivity, and they discovered that there were three main types of radioactivity, and they first discovered this by how deep these things could penetrate through material. And so they're like, okay, if some of this radioactivity doesn't go very far, some of it goes a little bit further, and some of it will go really far. And so they named them right away, alpha, beta, and gamma. First three letters of the Greek alphabet, because they knew there was three kinds of radioactivity. They still didn't know what they were, but they knew that alpha was the least penetrating of the three, beta would go a little bit farther, and gamma would go much farther through certain materials, whatever materials you wanted to. They did more experiments on the rocks and on the radioactivity, and they found that they couldn't alter the radioactivity by heating the samples or cooling the samples. Temperature didn't change it. High and low pressure did not affect it. Chemical treatments of the rocks did not change the radioactivity coming out of them. So they knew that whatever was happening with radioactivity was not a chemical process. It didn't have to do with the atoms and the electrons. It was something more fundamental than that, something deeper inside the atoms that couldn't be changed by pure chemical processes. You take a lump of uranium, you measure the radiation coming off of it. If you heat it up, same amount of radiation comes off of it. You pour hydrochloric acid on it, same amount of radiation comes off of it. Okay, so these mere chemical interactions weren't affecting the radioactivity. Something deeper was going on. Here's the thing that you and I should probably consider a little bit. A lot of people hear the term radiation, they get freaked out and like, oh, you think about the Incredible Hulk and stuff like that, right? And the reality is that radiation is a naturally occurring phenomenon. It exists everywhere. You are being bombarded by radiation right now. You are all your life. You can't avoid it, okay? The thing to be concerned about or think about is the level of radiation that you're exposed to, and that's where it gets dangerous. When you concentrate it, when you're exposed to a lot of radiation, then you start to see damaging effects. But right now there's radiation in this room coming off of those bricks off the wall. Some watches give off radiation if you have like little glowing hands on your watch. The earth itself, mountains particularly, if you live in a mountainous region, there's a lot of radiation coming off of the rocks of the mountains, stuff like that. So, I know. Okay, so let's look at this a little bit more closely then. Here are the three types of radiation when we're talking about nuclear radiation and the different penetrating depths. You do not need to memorize these depths, okay? But just to give you an idea of how they discovered there was three types. When they would shoot radiation at at something, well, this alpha radiation could barely even go through a piece of paper or even a little piece of aluminum foil. It would block the alpha particles. There was one particles that would get blocked by almost nothing, and they call those alpha. The beta particles could go through a little bit of metal and maybe a little bit of wood, and the gamma radiation could go through like 5 centimeters of lead. It was much more deeply penetrating, okay? They tried it in like water and flesh. I don't know if they actually tested flesh, but since we're mostly water, they're like, I wonder how much this stuff will penetrate us. Notice that alpha particles don't even go through your skin, a 3/100th of a millimeter. Like, so I could shoot you with my alpha ray gun, and you'd be like, aha, and it'd bounce right off of you. Okay, no problem. Wouldn't even hurt you. Okay. Beta particles could penetrate. They go a little bit farther, up to about 10 millimeters. And gamma rays, yes, they go a few meters in water. In the air, alpha particles will only go a few centimeters. That's the other reason if I'm shooting you with my alpha ray gun, you're sitting there laughing at me because it all like goes away after a couple centimeters. And beta particles, a few meters, and gamma rays will go like 100 meters through the air. Yeah, right.
What kind of
So after they looked at how deeply these things penetrate, they're like, what else can we learn? Why don't we shoot them through a magnetic field? Whew. If we shoot them through a magnetic field, what might we learn about them? If they're charged, because remember, they'll feel a force and they'll curve, right? So they did that experiment, and lo and behold, look what they found. They found 3 different paths of the 3 different kinds of radiations. So they take a big lead block, they throw a radioactive sample like radium in it. They knew radiation was coming off of that sample. Here's your magnetic field, and one of them would go straight. What does that tell you about the one that goes straight? No charge at all. One would curve to the left, one would curve to the right. Let's practice your right-hand rules. Notice this magnetic field is into the page. Please tell me with the right-hand rules, that alpha particle, which is bending to the left, is that positive or negative? Positive. And then by using the same right-hand rule, this beta particle is negative. Great. So they discovered that the alpha particles were positive and the beta particles were negative. Notice the radius of curvature. Notice the beta particles curve much more tightly than the alpha particles. So what could that tell you about those particles? One's more charged, one's moving less rapidly, or the mass is different. Okay, all those are valid conclusions. It turns out that mass is the main factor here, because these guys are much more massive than the beta particles. And they're more charged, actually, as well. They have twice the charge of a beta particle. Okay, so that was kind of cool. And let's start with alpha. Let's talk about what alpha radiation is, or alpha particles, okay? All an alpha particle is, well, first of all, we know it's positively charged. We know it's the least penetrating. And all it is a helium nucleus. It's a nucleus of a helium atom. It's 2 protons and 2 neutrons globbed together, moving at a relatively high rate of speed. It gets shot out of a larger nucleus, what we call the parent nucleus, and then that parent becomes something else, what we call the daughter nucleus, because it's lost 2 protons and 2 neutrons, because it's being shot out as an alpha particle. This process where an element turns into another element is called transmutation. And transmutation can happen naturally, but it can also happen artificially. There's natural transmutation, where an element just decays spontaneously by itself, and there's artificial transmutation, where humans come along, they do something to an element to make it turn into something else, and that's artificial transmutation. Let's look at an example. Okay, Ra226. Ra226. Sometimes it decays, and it becomes Rn222 and an alpha particle. This would be the parent product, Ra226. These are there's the daughter product and my alpha particle. Let me hand out. All right, so radium. What's the atomic number? Not the atomic mass, but the atomic number. 88. 88. And radon. 86. And helium. 2. So you guys, when you're doing this, when you're doing radioactive decay equations or nuclear equations, the math is relatively simple. You got a little arrow that's kind of like an equal sign in this world, and you guys probably did something like this in chemistry before, but notice that the numbers on the top have to add up on one side of the arrow compared to the other side of the arrow. So I started off with 226 nucleons. I ended up with 226 nucleons. I started off with 88 protons. I ended up with 88 protons, and everything's good. It's just that I had it in one nucleus, and it became 2 nuclei. This helium is traveling at real high speeds. Okay. When does alpha decay occur? More or less, it happens when the Coulomb force is greater than the strong nuclear force. Okay, when that repulsion between the protons is stronger than the strong, that's the Coulomb force, that electrostatic repulsion. When it's stronger than the strong nuclear force, then something's got to give, and what usually gives is a helium nucleus. It gets ripped out of there, ripped out of the nucleus. Now here's something we're going to be dealing with quite a bit in this unit. This is known as the Q value, or disintegration energy. Where does this energy come from? When that alpha particle gets shot off at real high velocities, it's got some energy, and we know that energy is conserved. But if we look really carefully at the masses of everything in the equations, if we compare the mass of the daughter products to the mass of the parent products, they won't be equal. They won't be equal. The daughter products will have less mass than the parent did. And some of that mass will have disappeared, and it will have become energy. And that energy is basically, it's mass becoming energy. And according to Einstein's equation, E equals mc squared. Okay? So for every little piece of mass that gets converted to energy, you have to multiply it by the speed of the light squared to figure out how much energy you get. So the consequence is a little bit of mass is a whole lot of energy. Okay? It's a huge amount of energy. Conservation of mass and energy. Okay? We could do the math here and figure out how much energy you get for every kilogram, but kilogram is a huge amount of mass. So on a nuclear level, we're usually going to be talking about atomic mass units. And if you do the math, you do the conversions, you end up figuring out that you get about 931.5 million electron volts for every atomic mass unit that gets converted to energy. That's an equation or a conversion factor that you will want to know. It is in your data booklet, but you need to know where to find it in your data booklet. Henry, did you have a question? You bet. And here's the thing about radioactivity, you guys. It's the kinetic energy. Well, let's just remind you at an electron volt. Electron volt's a really small unit of energy. It's equal to 1.6 times 10 to the negative 19th joules. It's basically how much energy it takes to move an electron through 1 volt of potential difference. Or if you allow an electron to fall through 1 volt of potential difference, that's how much kinetic energy that electron would gain. So it's a really small amount of energy, but you get 931.5 million of them for every atomic mass unit that you convert to energy. And that energy is in the form of kinetic energy. Here you have a stable nucleus sitting still, boom, the alpha particle comes off at real high speeds. That is what does the damage. The kinetic energy is what does the damage. It's the bombardment of these particles hitting your cells or hitting some other atom and ripping off electrons that does the damage. If the alpha particle is stationary, it's absolutely harmless. Or even at slow speeds, that's what helium is. You guys play with helium balloons all the time. And helium balloons are radioactive particles. I mean, helium nuclei, those are radioactive particles. Well, they're the same thing as an alpha particle. But when you're playing with them in a balloon, they don't hurt you. But when they go at really high speeds, they can be damaging. They can be dangerous. No, it is not because of that. Okay? So helium balloons are filled with the products of radioactive decay. All right? Okay. Let's do a little bit of practice. I don't know. Someone else was talking about that the other day. Okay, here we go. Let's try a little bit of practice. You guys have your periodic tables. I've got uranium-238. Let's assume that it decays and gives off an alpha particle. What will be the daughter product? Ready? Does that make sense how we did that, you guys? You just add the numbers up. Because I knew that alpha particle was 2 protons. I knew that uranium was 92 protons. So whatever I end up with has to have 90 protons. Yeah? And that tells me this. Well, the nucleons have to add up too. But the thing that determines what the element is the number of protons. Okay? All right, let's try another. Oh, by the way, you guys, this is an actual thing. It has a half-life of about 4.5 billion years. That means roughly if I had 100 uranium-238 nuclei, I'd have to wait about 450 billion years before those would have decayed. Half of them would have decayed. We'll talk about that. We're not there yet. Okay. Here's another practice. Give it a shot.
218.
All right. So everybody's getting polonium-218, hopefully. Understand how that works? Pretty straightforward. This has a half-life of 3.8 days. This is actually a much more radioactive material that radon-222 is than uranium-238. So, okay? All right. Easy stuff. We'll talk about half-life soon, okay? But let's go into beta decay. More specifically, beta negative decay. Beta decay is more penetrating than alpha decay. It is negatively charged, whereas alpha was positively charged. Since alpha is a helium nucleus, it has a charge of 2, like 2 fundamental charges, like 2 protons. Beta decay is kind of weird. Beta decay is an electron. However, it's an electron that comes out of the nucleus. Now, why is that strange?
Because electrons are the cloud around the nucleus.
And you've never heard of electrons being in the nucleus before, right? But beta decay is an electron that is shot out of the nucleus. It seems impossible, does it not? It's really, really strange. And here's kind of why. This is not exactly why, but if you think about it, a neutron is neutral. Wait, listen. A neutron is neutral. So one of the things, in order to conserve electric charge, if it wants to, it can become a proton and an electron. And we won't have violated the law of conservation of electric charge.
That's mass.
And, well, the masses are roughly the same. And actually, the energy that beta particle has, it all adds up. It just becomes a proton. No, so here's the thing. This is what you don't need. It's not correct to say that a neutron is made up of a proton and electron, because it's made up of quarks.
But it can just become.
But one of the quarks can change. And turn it into a proton.
What makes you decide to do that?
Frank down at the store just makes them decide. I don't know why they decided to do that, but it can happen. So this is where the electron comes from. When a neutron in the nucleus becomes a proton, it shoots off an electron at very high speeds, and we experience that as a beta particle. Okay. What's what? Yeah, so when a nucleus undergoes radioactive decay with a beta particle, notice a couple of things. When you give off an electron, the mass of the nucleus basically doesn't change. So the mass number stays the same. But you've gained a proton. So the atomic number increases by 1, but the mass number stays the same. Does that make sense? Because an electron is almost massless. It basically doesn't affect the mass of the nucleus. So the nucleus has gone up by an atomic number of 1 because suddenly there's another proton in it that wasn't there before. But the number of nucleons stays the same. All right. So for example, carbon-14 can become nitrogen-14 when it gives off an electron or a beta particle, and this third thing called an antineutrino. Okay. If we looked, what's the atomic number of carbon?
12.
6. The atomic number has 6 protons. What's the atomic number of nitrogen? 7. See how that works? Because an electron is kind of like, well, you can kind of think of this as like -1 and 0, kind of for the electron. It's kind of weird. All right.
Wait, yeah, so it's not like theoretical.
No. Well, I mean, yes, it was theoretical, but no, it's been totally proven and observed and measured.
That's not. Yeah, why is
Now, this is a relatively fascinating story. Okay, there were these two physicists named Wolfgang Pauli and Enrico Fermi, and back when they were doing stuff, this was back in the 30s, I want to say, 20s and 30s, the anti-neutrino and the neutrino didn't exist. But they knew about radioactive decay. And as they were exploring more and more decay and looking at energy conservation and momentum conservation, things weren't adding up. You could take this, for example, you could take this carbon nucleus, you could measure its momentum before it decayed, and then you could measure the momentum of these guys after they decayed, and they didn't add up. It wasn't conserved. And this was pretty cool. A lot of physicists were like, right on, we've actually violated the law of conservation of momentum. We've violated the law of conservation of energy. We've discovered something really new and fundamental. But Fermi and Pauli, okay, they were not willing to throw out those major laws of physics. They were not willing to say, you know what, the law of conservation of momentum is so fundamental, it is so enormous, that I think something else is going on there. And the law of conservation of energy, I think there must be some other particle that we don't know about that must be carrying away some energy. And they hypothesized it and called it the neutrino. They called it the neutrino for a variety of reasons. They assumed it had to be neutral, because otherwise we would have discovered it already, because charged particles are much easier to find than neutral particles. And they assumed it had to be really small. So neutrino means the little neutral one, the little neutral thing. Okay, they hypothesized this in like 1930, and it wasn't for 26 years before we actually discovered neutrinos. 26 years later, they were actually finally discovered. Nobel Prizes were handed out. People were like, woo, happy, happy, happy. Okay. So roughly speaking, again, these are generalities about why these things occur. But beta K tends to occur when it has too many neutrons compared to the number of protons, when it just needs to stabilize the ratio between neutrons and protons. And you know, that's obviously a very gross generalization, but it's a neutron turning into a proton, and there you go. Okay. Lastly is, what's that? Come on. Let's talk about gamma decay. The third of three. No, not yet. Gamma decay. Gamma decay. Gamma radiation is the most penetrating of the three, and it carries no mass and no charge. So this is the one that is actual electromagnetic radiation. The other two, alpha and beta, are actual particles. But then we'll get into the fact that particles aren't always particles, but that's a whole other story. So right now, just think of them as particles. And gamma radiation, you can think of it as like light, except for very high energy light. It's a little piece of light called a photon that is very, very high energy, more than visible light. It's at the very extreme energy end of the electromagnetic spectrum. This is as high as it goes, as far as we know. It's basically a photon with very high energy. You guys know now that high energy photons have very small wavelengths and very high frequencies, because E equals HF. We'll talk more about that in a little bit down the road. Okay. The gamma radiation is emitted when a nucleus drops from a higher energy state to a lower energy state. Okay. Last class we were talking about visible light. Remember spectral lines being given off when electrons dropped orbitals. So visible light lines, the spectral lines that are visible, those are lower energy because the electron orbitals are lower energy transitions. If the nucleus undergoes an energy transition, it's a much higher energy, and that's why it gives off a gamma ray instead of a visible light photon. It gives off a gamma photon. Okay? The nucleus doesn't change otherwise. You don't lose any protons, you don't lose any neutrons, you just go from a higher energy state to a lower energy state. And a lot of times they'll say it basically, it's an excited nucleus and it drops down to a lower energy state and gives off a gamma ray photon.
Seems so simple.
All right, so here's your summary. Here's your summary of the three types of radiation. Alpha, beta, gamma, you should know this. You should basically, get this figured out. But alpha particle is just a very fast helium nucleus, a beta particle is a very fast electron, and a gamma ray is a very fast piece of light, okay, which is really fast, speed of light, as fast as you can go. How much charge do they have? Alpha has a charge of +2, which is like +2 protons. Beta is -1, just like an electron, and gamma is not charged at all. Mass, and in terms of atomic mass units, 4 for the alpha, almost nothing, and then definitely nothing. And then the speed of light. So alpha particles go like 3 to 8% the speed of light, which you're like, well, that's wimpy. Look, the gamma ray goes 100% the speed of light. But even 3% the speed of light is an enormously fast speed for you and I. It's way, the fastest things we've ever gone are like 100th% of the speed of light in terms of like objects. In terms of, well, not, I shouldn't say that. In particle accelerators, we've gone really fast, but in terms of like spaceships and stuff that people could ride on. You know what I mean? Okay. Okay. Let's do a little practice. Here we go. Practice, practice, practice.
Hey, practice.
Polonium-218 gives off a beta particle. And there you go. Let's try another one. Ooh, how about this one? We're working backwards. What is the parent product that creates a beta particle and polonium-214? What is the parent product? Is it? Is it?
No, it's bismuth.
Bismuth? Yeah, there you go. Yes, there should be an antineutrino with all of these. So this should have an antineutrino. I think that's the antineutrino, actually. Antineutrino. The electron is the beta particle. Okay. One more. Okay, let's practice alpha backwards. So what is the parent product that gives off an alpha particle and becomes lead-206? It's something 210, but what is it?
Po.
Okay.
Po.
Okay.
How did you know?
Because you know that because the alpha particle has it's 2, 4, and whatever that is. What's lead? The atomic number?
82. And you want 82.
82.
Po.
So this thing has to be 84.
You would have to know that lead is 82.
Yeah, exactly. Okay. And I don't expect you to memorize that, but you should be able to use the periodic table and figure that out. Okay. All right. So those are the 3 types of radiation. And I want to go back to this idea. So radiation is naturally occurring. It is everywhere. Again, it's the concentration of radiation that is damaging. And so we've come up with a unit to try to kind of create that, because you've got 3 kinds of radiation. Some of them are penetrating the others. Here's the deal. Gamma rays are dangerous because they actually can penetrate pretty deeply. Alpha particles are the biggest of the 3. And the way these things are damaging is by colliding with other atoms, okay? And so the biggest one, the alpha particle, if it can get in there and make some collisions, it's the most dangerous, and that's why it doesn't go very far. So they've tried to level the playing field and be really clear about how can we just express the damaging effects of radiation. So they came up with this unit, the REM. And you might have heard of, you measure REMs, it's basically telling you how much exposure you've had to a certain amount of radiation. It's a unit that allows you to find the damage regardless of which type of radiation it is, okay? So, just to give you some rough ideas, 5 REMs, 5,000, that's okay, you guys, this is, so like 5,000 millirems or 5 REMs, it wouldn't even hurt you. You wouldn't notice much, okay? But you get up to 100 REMs, you start having some nausea, maybe vomiting for a couple days, temporary drop in blood cell production, but then you'd bounce back and you'd be totally fine. If you're exposed to 350 REM, okay, nausea and vomiting initially, followed by a period of apparent wellness. After 3 to 4 weeks, you might get infections and bleeding due to white blood cells and platelets. Medical care would be required, and then higher levels of exposure can be fatal. So that's kind of how it's measured. Again, it doesn't matter which radiation. The REM is a unit that's kind of canceled that all out. So let's take a look